Thank you for a kind introduction. I'm Sangun Choi from Korea University. I'm happy to present our work called Kubism, Disassembling and Reassembling K-means clustering for mobile heterogeneous platforms. K-means clustering is a cornerstone of many data analysis applications in embedded systems. K-means clustering involves distance calculations between numerous data points and centroids over multiple iterations. This behavior makes the clustering process highly parallelizable. Also, prior work has proposed Yunho K-means clustering algorithm to reduce the computational workload. This algorithm identifies and skips unnecessary distance calculations that do not affect the clustering state. This figure shows a simplified example of Yunho K-means clustering. At the start of an iteration, data points are clustered into two clusters. For each pair of data point and centroid, the algorithm first determines if the distance calculation is skippable. If the calculation is not skippable, the algorithm performs computation. After the distance calculation, the algorithm reassigns clusters based on the calculated distances. However, running Yunho K-means clustering on embedded systems faces two significant challenges. First, the skipping mechanism incurs warp divergence, thus underutilizing GPU resources. Also, existing algorithms do not utilize CPU for distance calculation, which account for most of the execution time. So, our goal is to efficiently utilize both CPU and GPU to address these challenges. With this objective, we propose Kubism, designed to improve hardware utilization and overall performance. The presentation is organized as follows. First, I'll explain the motivation of our research and introduce our solution, Kubism. After that, I'll present the evaluation results and finish the presentation with our conclusion. K-means clustering offers high parallelization opportunities, and this figure shows how a GPU performs distance calculations in parallel. Each GPU thread handles one data point and sequentially calculates distances to every centroid. However, with the skipping mechanism, only a few threads within a warp performs distance calculation while others wait. This behavior is known as warp divergence. And this figure shows an example of how warp divergence occurs. In this example, there are 4 data points and 5 centroids, and 4 GPU threads performs distance calculation in parallel. And for the first centroid, each GPU thread checks if the distance calculation is skippable. In this example, only thread 1 performs distance calculation while others wait. Similarly, for the second centroid, only thread 2 performs computation while others remain inactive. The algorithm repeats this process for all subsequent centroids. As a result, a GPU suffers from severe warp divergence. And we provide the number of active threads within a warp during the clustering process. This metric represents the average number of threads that actually perform distance calculation within a warp. So the maximum value is 32. This table shows a ratio of skipped distance calculations and number of active threads and the portion of inactive threads within a warp for 5 iterations. For the first 2 iterations, 91% and 60% of threads remain inactive respectively. Since these iterations have relatively high skip ratios, a GPU suffers from a significant warp divergence. Also, embedded systems can further leverage this parallelism by utilizing CPUs. By collaboratively using CPU, a system can reduce the computational workload assigned to the GPU. And the architecture of embedded platforms also provide advantages. In these platforms, CPU and GPU physically share a device memory. This structure eliminates the overhead of explicit data copy between CPU and GPU. Therefore, a parallel execution of K-means clustering using both processors is a promising approach for acceleration. However, existing algorithms do not utilize CPU for most of the execution time. These algorithms only utilize CPU for a limited number of tasks, such as kernel launch and cluster assignment. Our profiling results show that CPU remains idle for 90% of the end-to-end execution time. These observations show that existing K-means clustering algorithms inefficiently use the hardware resources of embedded platforms. Now, I'll introduce our solution, Kubism. Kubism consists of three main stages called clustering reordering, warp balancing, and task distribution. Let me explain these techniques step by step, starting from the clustering reordering. And this figure shows the original Inyan K-means clustering algorithm. This algorithm iteratively checks if the calculation is skippable and then performs computation. In contrast, Kubism first identifies all skippable distance calculations before the computation. Through this process, Kubism can proactively determine the skip ratio and gather information about which distance calculations are necessary. Kubism uses this information to guide the distance calculation phase. In this phase, Kubism employs two core techniques called warp balancing and heterogeneous platform-aware task distribution. During the early identification of skippable calculations, Kubism generates metadata as shown in the left figure. In this metadata, rows represent data points and columns represent centroids. And for each element, 1 indicates the necessary distance calculation and 0 indicates the skippable distance calculation. And each thread uses this metadata to fetch the index of centroid required for distance calculation. And then thread perform only necessary distance calculations, making all threads within a warp actively compute. Similarly, for the next step, each thread fetches the next index of centroid required for distance calculation and then performs computation. Through this warp balancing, Kubism increases the number of active threads within a warp and accelerates the distance calculation phase. This warp balancing technique is effective in iterations with high skip ratios. However, if a skip ratio is low, warp divergence has a minimal impact on performance, and the overhead may outweigh the benefits. To address this challenge, Kubism incorporates a dynamic skip ratio decision technique. First, Kubism sets a threshold of skip ratio where the warp balancing is expected to be beneficial. This figure shows how Kubism sets this threshold. Before the computation, Kubism first predicts the execution time of current iteration, and Kubism uses the skip ratio and the execution time of previous iteration along with the skip ratio of current iteration. This approach relies on two insights. First, the execution time of an iteration is proportional to the number of distance calculations. Second, the number of distance calculations can be estimated through the skip ratio. After the distance calculation, Kubism compares the actual execution time with the expected value. If the actual execution time is longer than expected, Kubism determines that the warp balancing does not improve performance in current skip ratio. Therefore, Kubism sets the current skip ratio as the skip ratio threshold. Then, for subsequent iterations, Kubism performs the warp balancing only if the skip ratio is higher than this threshold. After this selective warp balancing, Kubism distributes the distance calculations between CPU and GPU. This figure shows an example of this task distribution. In this example, there are 4 tasks, each representing distance calculation. Kubism first distributes these tasks according to a predetermined task partitioning ratio. Since the GPU has a higher throughput than CPU, Kubism assigns more tasks on the GPU side. And after the distance calculation, Kubism adjusts this partitioning ratio based on the execution times of both processors so that both execution times become similar. This task distribution accelerates the k-means clustering by effectively using both processors. Now, I present our evaluation results for Kubism. We conduct all experiments on the NVIDIA Jetson Orin platform, which is an embedded GPU with 8 SMs and a 12-core CPU. We compare Kubism with the prior GPU-based implementation of Inyan k-means clustering, which serves as a baseline. And we configure another technique called WB plus HETD to evaluate the effectiveness of our selective warp balancing technique. Unlike Kubism, this technique consistently applies the warp balancing and task distribution without considering the potential overhead of warp balancing technique. And we configure 9 datasets to examine the effects of various structures of real-world datasets. We select 3 numbers of data points and feature dimensions, then combining them to build the dataset. And this graph shows the geometric mean of end-to-end speedup over the baseline. Kubism achieves a 23% performance improvement by improving the GPU thread efficiency and utilizing CPU and GPU effectively. To further analyze the performance, we conduct a case study for 3 individual iterations with varying skip ratios. In this graph, the x-axis shows the skip ratios and the y-axis shows speedup over the baseline. And if the skip ratio is close to 1, the warp balancing technique significantly improves the performance. However, if a skip ratio is 0, the warp balancing incurs a significant overhead while providing no performance improvement. As a result, WB plus HETD shows lower performance than the baseline. Kubism does not perform the warp balancing in such iterations, showing performance improvements in all cases. And so these results show the necessity and effectiveness of our selective warp balancing technique. And we profile the hardware utilization during the clustering process for the baseline and Kubism. The table above shows the number of active threads per warp during the clustering. And Kubism achieves up to 3.3 times higher active thread than the baseline. And this achieving 9.1 active thread is a significant improvement considering the fundamental differences in the number of distance calculation assigned to each GPU. If a skip ratio is high, the variance of distance calculations for each thread increases. So even with our warp balancing, the thread with the most distance calculation becomes the critical path within a warp, making some thread remain inactive. So despite the warp balancing, the number of active threads is lower than 32. And the table below shows the average CPU utilization during the end-to-end clustering process. While baseline shows only a 10% CPU utilization, Kubism achieves a 77% CPU utilization. So these results highlight again our key message that efficient use of hardware resources is a key to improving performance. So in conclude, running K-means clustering on embedded systems faces two primary challenges. The skipping mechanism incurs a significant warp divergence, and existing algorithms do not utilize CPU for distance calculation. We propose Kubism that improves both CPU and GPU utilization and accelerates K-means clustering on embedded systems. Yeah, so thank you for your attention, and I'd be happy to answer any question.
Thank you. Any questions, comments from the audience? Yes, please.
I have two quick questions. So for running the some portion of the program in the CPU, what kind of code is running? It should not be CUDA.
Yeah, we implement the Inyan K-means clustering code in C and running in the host CPU.
How well optimized of the CPU-based code?
You mean the compiler optimization level, or?
No, in general, it is the general comment, general question.
Yeah, we think we implement the CPU code to utilize the most of CPU cores, and yeah, so I cannot capture the meaning of optimization exactly. Yeah.
Okay. Another question is how big is the portion of the workload to be executed in CPU?
So the question is the portion of K-means clustering distance calculations running on CPU.
Yes.
Yeah. Typically, we run the 20% of distance calculations in CPU. Yeah.
All right, let's thank our speaker again.
Thank you.
Yes.